Have you ever looked up at the night sky and felt that overwhelming sense of wonder, that tingling curiosity about where all of this, the stars, the planets, the vast emptiness between them, where did it all come from? You're not alone. For as long as humans have existed, we've gazed at the heavens and asked the same profound question: how did the universe begin? It's a mystery that stretches back to the very dawn of human thought, from the creation myths of ancient civilizations to the mind-bending theories of modern physics. And here's the incredible part: we're living in an era where science is closer than ever to uncovering the answers. Think about it for a moment. Every atom in your body, every speck of dust on your shelf, the very screen you're staring at right now, all of it traces back to a single, unimaginable moment nearly 14 billion years ago. A moment when time, space, and energy burst into existence in a cosmic event so powerful, its echoes still ripple through the universe today. But what exactly happened in those first fleeting seconds? How did a universe of infinite complexity emerge from what scientists believe was a speck smaller than a single grain of sand? The story of our cosmic origins is stranger than fiction, filled with explosive beginnings, mysterious forces, and discoveries that continue to rewrite our understanding of reality itself. This isn't just a story about the past, it's a journey that connects us all. Because when we unravel the secrets of the universe's birth, we're also uncovering clues about our own place in the cosmos. From the mind-boggling concept of the Big Bang to the cutting-edge theories that push the boundaries of physics, we're about to explore the most awe-inspiring ideas science has ever conceived. So settle in, because by the end of this journey, you won't just see the night sky the same way again, you'll feel it. The universe has a story to tell, and it's time we listened. The Big Bang Theory isn't just some wild guess, it's the most compelling explanation we have for how everything around us came to exist. Picture this: nearly 14 billion years ago, the entire universe was compressed into a point so unimaginably small and hot that the laws of physics as we know them break down when we try to describe it. Then, in less than a blink of an eye, this tiny speck underwent an expansion so rapid it defies intuition. Space itself stretched, carrying matter along with it like raisins in rising dough. This wasn't an explosion outward into emptiness because there was no outside yet. Instead, space and time were born in that very instant, unfolding like a cosmic tapestry that's still expanding today. But how do we know this actually happened? The evidence is etched into the universe itself. Take cosmic microwave background radiation, the faint afterglow of that primordial fireball. It's everywhere, bathing the cosmos in a uniform whisper of heat left over from when the universe was just 380,000 years old. Then there's the abundance of light elements like hydrogen and helium, forged in those first fiery minutes. The ratios we observe in stars and galaxies match precisely what the Big Bang predicts. Even the way distant galaxies are racing away from us, their light stretched into redder wavelengths, tells us the universe is still stretching, carrying the echoes of that initial expansion. What's truly mind-bending is how much happened in those first fleeting moments. Within the first second, the universe cooled enough for subatomic particles to form, then atoms, and eventually the seeds of galaxies. Gravity began sculpting the cosmos, pulling matter into the structures we recognize today. And here's the wild part: we're still inside that expansion. The Big Bang wasn't an event that happened somewhere out there. We're literally riding the aftermath of it, part of an ongoing story that began when time itself flickered into existence. Every time you look up at the stars, you're seeing snapshots of that ancient light, pieces of a puzzle that scientists are still putting together. But that initial expansion after the Big Bang, It wasn't just fast, it was downright explosive. In a fraction of a second so small our brains can't even process it, the universe underwent something called cosmic inflation. Imagine blowing up a balloon to the size of a grape and then, in less time than it takes to snap your fingers, that balloon inflates to be larger than our entire observable universe. That's the scale we're talking about. Space didn't just grow, it stretched at a rate so extreme, it would make even the fastest rockets look like they're standing still. This wasn't just wild growth for growth's sake. Inflation solved some of the biggest mysteries about our universe. Take its uniformity, for example. No matter which direction we look, the cosmic microwave background, that ancient afterglow, is almost perfectly even. Without inflation, that smoothness makes no sense. Distant regions of space shouldn't have had time to even out their temperature, yet they did. Inflation explains why. Those areas were once cozy neighbors, pressed together before the universe stretched them apart in that sudden burst. But here's where it gets even stranger. Tiny quantum fluctuations, random ripples in space smaller than atoms, got magnified to cosmic proportions during inflation. Those microscopic wrinkles became the seeds for everything we see today. The slightly denser patches pulled in more matter through gravity, eventually growing into galaxies, stars, and the vast cosmic web we observe. Without those quantum whispers stretched across the universe, matter might have been spread too thin, leaving space empty and dark. Yet despite how well inflation fits the evidence, we still don't know what powered it. Some hidden field of energy, a phase transition in the fabric of reality. Whatever it was vanished almost as quickly as it appeared, leaving behind an expanded universe cooling into the familiar laws of physics. Scientists hunt for clues in the faint patterns of the cosmic microwave background, hoping to catch echoes of that primordial stretch, because if we can understand inflation, we're peering into the universe's very first moments, a time when the rules we take for granted were still being written. That unimaginable heat of the early universe wasn't just empty energy, it was a seething ocean of potential, waiting to transform into the very first bits of matter. As the cosmos expanded and cooled to around a quadrillion degrees within mere microseconds, something remarkable happened. The energy that had dominated those first moments began condensing into particles so tiny they defy imagination: quarks and leptons. These weren't just any particles, they were nature's ultimate building blocks, the smallest known pieces of reality that would eventually construct everything from stars to smartphones. Picture a cosmic soup so dense and energetic that particles flickered in and out of existence, constantly forming and annihilating in a frenzied dance. Quarks, those hyperactive specks with whimsical names like up, down, and strange, couldn't even exist alone at first. They zipped around in trios, bound by an unimaginably strong force we now call the strong nuclear interaction. Meanwhile, their lightweight cousins, leptons, including the familiar electron, zipped through this primordial plasma, nearly massless at these extreme energies. What's astonishing is that for every particle created, an antiparticle emerged too, its mirror opposite in charge. Most annihilated each other instantly in bursts of energy, but by some cosmic fluke, 1 in every billion particles survived. That tiny excess is why we have matter today instead of an empty void. As the universe kept cooling, something even more pivotal occurred. Those hyperactive quarks began slowing down enough to stick together, forming the first stable protons and neutrons. This happened when the cosmos was about 1/1,000,000th of a second old, a blink so fast. If you slowed it down to a full second, all of human history would stretch over trillions of years. The protons and neutrons we know today are essentially triplets of quarks locked in an eternal embrace. 2 up quarks and 1 down make a proton, while 2 downs and an up form a neutron. Their slight differences in composition explain why protons carry positive charge while neutrons stay neutral, a delicate balance that would later allow atoms to exist. But here's where it gets even more fascinating. The leptons, especially electrons, played an equally crucial role. While quarks built atomic nuclei, electrons would eventually orbit them, completing the structure of atoms. Yet in these early moments, electrons were trapped in a constant battle with their antimatter twins, positrons. Only when the universe cooled further, allowing matter to dominate over antimatter, did electrons break free to become the glue of chemistry. This transition didn't just create matter, it set the stage for every structure we see today, because without that precise balance between quarks forming nuclei and electrons orbiting them, there would be no atoms, no molecules, no planets, and certainly no curious creatures like us pondering how it all began. What's truly humbling is realizing that every object you've ever touched, every breath you've taken, is made possible by these microscopic survivors from the universe's first chaotic moments. The iron in your blood, the silicon in your phone, the oxygen filling your lungs, all of it traces back to particles that emerged when time was still young, and the cosmos was forging the very rules of existence. For nearly 400,000 years after the Big Bang, the universe remained too hot and chaotic for atoms to exist. Picture a thick, glowing fog where free electrons zipped around at blinding speeds, constantly scattering photons, particles of light, preventing them from traveling any meaningful distance. But as expansion continued, the cosmos gradually cooled to around 3,000 degrees, finally allowing something extraordinary to happen. Electrons, exhausted by their frantic dance, slowed down just enough to be captured by atomic nuclei, a pivotal moment called recombination. This wasn't just a minor shift, it was the universe's first breath of clarity. For the first time, protons could hold onto electrons, forming complete hydrogen atoms. Helium nuclei, forged in the earlier nuclear reactions, also grabbed their electrons, becoming stable atoms. Suddenly, light could travel unimpeded through space. Those once trapped photons burst free in a brilliant flash, creating what we now detect as the cosmic microwave background, a snapshot of the universe's infancy. But why hydrogen and helium? In those early moments, conditions were perfect for only the simplest elements to form. Hydrogen, with its single proton and electron, was nature's easiest atomic structure. Helium, slightly more complex but still lightweight, formed when pairs of protons and neutrons locked together. Everything heavier would require the extreme environments of stars, and those didn't exist yet. These newborn atoms didn't just float aimlessly. Tiny density variations left over from inflation caused hydrogen and helium to clump together under gravity's pull. Over millions of years, these gas clouds would collapse further, growing hotter and denser until nuclear fusion ignited inside them, giving birth to the first stars. Without those initial atoms, the universe would have remained a dark, featureless void. Every galaxy, every planet, every living thing owes its existence to that critical transition when chaos settled just enough to let matter and light finally take shape. What's astonishing is how delicate this balance was. If recombination had happened earlier, heavier elements might never have formed later, and the universe might have expanded too rapidly for stars to gather. Instead, conditions aligned perfectly to create a cosmos rich with possibility, one where simple atoms became the foundation for everything we know. After the glow of recombination faded, the universe entered an era unlike any other, a time of profound darkness that stretched for millions of years. Imagine a cosmos without a single source of light, no twinkling stars, no swirling galaxies, just an endless sea of hydrogen and helium gas, drifting silently through the expanding void. This was the Cosmic Dark Ages, a chapter so obscure that even our most powerful telescopes struggle to peer into its shadows. But why was it so dark? The answer lies in the absence of stars, those cosmic furnaces that turn matter into light. After recombination, the universe had cooled too much for nuclear fusion to occur spontaneously. The gas clouds were too diffuse, too evenly spread, leaving nothing to break the monotony of the expanding darkness. Yet beneath this stillness, something invisible was at work: gravity. Tiny ripples in the gas left over from those quantum fluctuations during inflation slowly gathered mass, pulling atoms together in an agonizingly slow dance. What's astonishing is how fragile this process was. If gravity had been just slightly weaker, matter might never have clumped together. Too strong, and the universe could have collapsed back on itself before stars had a chance to form. Instead, gravity worked at precisely the right pace, sculpting denser pockets of gas over eons until at last the first protostars began taking shape. These weren't like the stars we know today. They were monstrous behemoths, hundreds of times more massive than our sun, burning furiously hot and living short, violent lives. And then light. When the first star finally ignited, it didn't just pierce the darkness, it shattered it. Ultraviolet radiation poured into the surrounding gas, stripping electrons from atoms and ending the cosmic dark ages in a blaze of rebirth. These pioneering stars didn't just illuminate the universe, they transformed it. Their nuclear hearts forged heavier elements: carbon, oxygen, nitrogen, seeding the cosmos with the raw materials for planets, life, and eventually us. Think about that for a moment. Every element in your body, other than hydrogen, was forged inside stars. The calcium in your bones, the iron in your blood, even the silicon in the device you're using right now. All of it was scattered into space by stellar explosions, recycled over billions of years until it became part of you. The Dark Ages weren't just an empty pause in cosmic history. They were the quiet before a storm of creation, a necessary lull that set the stage for everything that followed. Without that long night, the universe might have remained forever dark. Instead, gravity's patient work lit the spark that would eventually fill the cosmos with light. Those first stars didn't just break the cosmic darkness, they rewrote the rules of the universe. Known as Population 3 stars, these primordial giants were unlike anything we see today. Imagine spheres of pure hydrogen and helium, hundreds of times more massive than our sun, burning at temperatures so extreme they would make modern stars seem like faint candles. With no heavier elements to slow their nuclear reactions, they lived fast and died young, blazing through their fuel in just a few million years, a cosmic heartbeat compared to our sun's 10 billion-year lifespan. Inside their searing cores, something miraculous unfolded. For the first time since the Big Bang, atoms heavier than helium were being forged. Through a process called stellar nucleosynthesis, hydrogen fused into helium, then under incredible pressure and heat helium atoms smashed together to form carbon and oxygen. These weren't just new elements, they were the building blocks of future worlds, but the real magic happened when these stars met their spectacular ends. Without the stabilizing influence of heavier elements, Population 3 stars were destined for cataclysmic supernova, explosions so powerful they briefly outshone entire galaxies. In their final moments, these dying giants performed the universe's first act of cosmic recycling. Shock waves from their explosions hurled newly formed elements across interstellar space, mixing them with surrounding gas clouds. This stellar alchemy transformed the chemical makeup of the cosmos, enriching future generations of stars and planets with carbon, oxygen, and other essential ingredients. Every rocky planet, every breathable atmosphere, every molecule in your body contains atoms forged in those first stellar furnaces. What's truly astonishing is how delicate this process was. If those early stars had been slightly less massive, they might not have reached the temperatures needed to create heavier elements, more massive, and they could have collapsed directly into black holes without scattering their precious cargo. Instead, they struck a perfect balance, cosmic artisans crafting the raw materials for everything to come. Today, we see their legacy in the oldest stars of our galaxy, which contain trace amounts of elements spilled by those first, long-vanished giants. Yet population 3 stars remain elusive. No telescope has directly observed one. Their light is too faint and distant. But astronomers hunt for clues in the chemical fingerprints of later stars, in the faint afterglow of ancient supernovae, and in the deepest reaches of space where some believe a few of these relics might still linger. Finding one would be like uncovering the universe's birth certificate, a direct window into the era when darkness gave way to light, and the cosmos took its first steps toward complexity. Think about this the next time you look at a tree or a mountain or your own hand. The calcium in your bones, the iron in your blood, the silicon in Earth's crust, all of it was once stardust, forged in hearts of stars that died before our solar system even existed. We are quite literally made of the remnants of those first cosmic beacons, the children of starlight that refused to fade into darkness. Gravity's patient work didn't stop with the first stars. It had a far grander vision in mind. Over hundreds of millions of years, those scattered stars and clouds of enriched gas began gathering into something even more spectacular, the first galaxies. Picture vast cosmic whirlpools, each containing millions or even billions of stars, all bound together by the invisible threads of gravity. But these weren't the elegant spirals or glowing ellipticals we see today. The earliest galaxies were messy, chaotic places, clumps of stars and gas colliding, merging, and reshaping themselves in a violent dance of creation. What held these fledgling galaxies together? The answer lies in one of the universe's greatest mysteries, dark matter. Though invisible and undetectable by conventional means, this strange substance outnumbers ordinary matter 5 to 1. Its gravitational pull acted like scaffolding, drawing gas and stars into dense knots while ordinary matter swirled into disks and halos. Without dark matter's unseen grip, galaxies might never have formed, or they would have flown apart as soon as they spun into existence. Our own Milky Way tells the story of this gradual evolution. It began as a modest collection of stars and gas over 13 billion years ago, growing through countless mergers with smaller galaxies. Some of its oldest stars, found in the halo surrounding the galactic disk, are ancient relics from those early days, celestial fossils preserving the chemical signature of the universe's youth. Over time, gravity shaped the Milky Way into the majestic spiral we recognize today, with its swirling arms, glowing core, and a supermassive black hole silently anchoring the chaos. But galaxies didn't just form in isolation. They clustered together, drawn into vast webs by gravity's unrelenting pull. Some settled into dense groups, like the Virgo cluster with its 1,000 galaxies, while others drifted in quieter cosmic neighborhoods. These structures, filaments and voids stretching across billions of light-years form the universe's large-scale architecture, a tapestry woven by gravity over eons. What's astonishing is how much diversity emerged from such simple beginnings. From the tiniest dwarf galaxies, barely holding a few million stars, to colossal ellipticals like Messier 87, home to trillions of stars and a black hole famous for its first ever photographed shadow, each galaxy carries the imprint of its unique history. Some, like our Milky Way, continue to evolve, cannibalizing smaller neighbors and birthing new stars. Others, in crowded galaxy clusters, have grown old and quiet, their star-forming gas stripped away by violent encounters. Yet every galaxy, no matter its shape or size, shares the same origin story. A humble beginning in the aftermath of the Big Bang, a slow gathering of stardust, and the patient, invisible hand of gravity sculpting chaos into cosmic beauty. When you look up at the night sky, you're not just seeing stars, you're glimpsing the end result of billions of years of gravitational artistry, a masterpiece written in light and dark matter across the canvas of space. Imagine building a house without ever seeing the frame. That's the puzzle scientists face with dark matter. It doesn't emit, absorb, or reflect light, making it completely invisible to every telescope we've ever built. Yet its gravitational fingerprints are everywhere. When astronomers measure how galaxies spin, they find stars orbiting at speeds that should fling them into space unless some unseen mass is holding them together. When they map the cosmos's large-scale structure, they find galaxies clustered in ways that ordinary matter alone couldn't explain. Dark matter is the hidden scaffold of the universe, an invisible hand that's been shaping cosmic architecture since the beginning. Here's what makes it so baffling. We know what dark matter does, but not what it is. Ordinary matter, the stuff of planets, stars, and people, makes up less than 5% of the universe's total content. Dark matter outweighs it 5 to 1, yet it refuses to interact with light or any known particle except through gravity. Some theories suggest it could be WIMP, weakly interacting massive particles left over from the Big Bang. Others propose actions, hypothetical particles so lightweight they'd flow through you like a breeze through a screen door. There's even the wild idea that dark matter might be primordial black holes, forged in the universe's first chaotic seconds. The hunt for dark matter is one of science's greatest detective stories. Deep underground, detectors wait for the faintest bump of a dark matter particle passing through. In space, telescopes scan for gamma rays that might signal dark matter annihilations. Particle accelerators recreate extreme energies, hoping to produce something, anything, that matches predictions. So far, the mystery endures, but every null result narrows the possibilities, inching us closer to an answer. What's truly humbling is realizing how much of the universe remains hidden from us. Dark matter doesn't just shape galaxies, it dictates their fate. Simulations show that without its gravitational glue, galaxies would never have formed in the first place. Even now, vast halos of dark matter surround every galaxy, their gravity bending light in ways we can measure but never see. We're like sailors navigating by the stars, unaware of the ocean currents beneath us. Yet understanding dark matter isn't just about solving a cosmic riddle, it's about rewriting the story of how everything, including us, came to be, perhaps the most poetic twist. Dark matter's invisibility is what makes it so essential. If it interacted with light, it might have clumped too tightly in the early universe, disrupting the delicate balance that allowed stars and galaxies to form. Instead, its silent presence created the perfect conditions for complexity to emerge. Every galaxy, every planet, every life form owes its existence to this enigmatic substance, proof that sometimes the most powerful forces are the ones we can't see at all. Just when we thought we had the universe figured out, it threw us another curveball, one so baffling it makes dark matter seem almost ordinary. In the late 1990s, two teams of astronomers made a discovery that would upend cosmology. The universe isn't just expanding, it's accelerating. Imagine tossing a ball into the air, only to watch it shoot away faster and faster instead of falling back down. That's the eerie reality we're facing with dark energy, a mysterious force pushing galaxies apart at speeds that defy gravity's pull. What makes dark energy so unsettling is how little we understand it. unlike dark matter, which sculpts galaxies through gravity, dark energy behaves like an anti-gravity force woven into the fabric of space itself. Think of empty space not as nothingness, but as a stretching rubber sheet, except someone keeps cranking the tension tighter. This bizarre effect accounts for a staggering 68% of the universe's total energy, dwarfing both dark and ordinary matter combined. Yet despite its dominance, dark energy leaves no trace except its cosmic fingerprints, distant supernovae appearing dimmer than they should, galaxy clusters drifting apart faster over time, and subtle wrinkles in the universe's large-scale structure. The leading theory that dark energy is the cosmological constant, a term Einstein once called his greatest blunder, representing a steady energy density inherent to space. But here's the twist: some data suggests dark energy might not be constant at all. What if it's grown stronger over billions of years or fluctuates like some cosmic tide? Alternate theories propose exotic fields or even modifications to Einstein's gravity itself. The stakes couldn't be higher because dark energy doesn't just push galaxies away, it dictates the universe's ultimate fate. A constant dark energy leads to a quiet, icy expansion where galaxies vanish beyond our horizon. A growing one could rip apart everything from stars to atoms in a catastrophic Big Rip. Yet for all its mystery, dark energy might hold clues to an even deeper truth. Its discovery revealed how much of the universe remains hidden in plain sight, governed by forces we're only beginning to name. Every time astronomers measure the heavens, they're not just mapping stars, they're deciphering a cosmic tug of war between darkness and light, gravity and antigravity, unfolding on scales so vast they humble human imagination. And somewhere in that tension lies the answer to the universe's greatest question: how does this story end? The universe isn't just a scattering of galaxies, it's a grand, intricate tapestry woven from threads of light and dark matter, stretching across billions of light years in a pattern so vast it defies human scale. Picture standing in a dense forest at night, holding a flashlight that only illuminates the nearest trees. Now imagine that forest spans the entire planet, with trees clustered along invisible paths and enormous empty clearings between them. That's the cosmic web, a labyrinth of galaxy-filled filaments intersecting nodes and hauntingly empty voids, all tracing the hidden blueprint of the cosmos. This colossal structure didn't form by chance. It's the result of a tug of war between gravity's relentless pull and dark energy's mysterious push. In the early universe, tiny density fluctuations left over from quantum ripples during inflation gave gravity something to work with. Over billions of years, dark matter's invisible scaffolding anchored these irregularities, pulling gas and galaxies into sprawling threads. Meanwhile, dark energy stretched the space between them, accelerating the expansion and carving out voids so empty they'd make a black hole seem crowded. What's astonishing is how perfectly this web mirrors simulations of cosmic evolution. Supercomputers crunching the laws of physics generate virtual universes that look eerily like our own, with galaxies clustering along filamentary intersections, just as we observe. The largest of these nodes, like the Laniakea supercluster home to our Milky Way, contain hundreds of thousands of galaxies bound together in a gravitational dance. Yet even these immense structures are mere threads in a web spanning hundreds of millions of light years. But how do we map something so vast? Astronomers use ingenious tricks, like measuring galaxy redshifts to plot their positions in 3D space, or studying the cosmic microwave background for imprints of early density variations. Some even trace the web indirectly by observing how light bends around invisible dark matter filaments, a phenomenon called weak gravitational lensing. Each method reveals another piece of the puzzle, showing how galaxies align like pearls on a string, drawn together by forces we're only beginning to understand. The cosmic web isn't just a static relic, it's still evolving. Galaxies flow along filaments like water down a river, funneling toward dense clusters where they collide and merge. Voids grow emptier as dark energy stretches them wider, while filaments stretch and thin like taffy pulled too far. Every snapshot of this web captures a moment in a story that began with quantum whispers and will end in a fate still unknown. What's humbling is realizing that our entire visible universe might be just one knot in this infinite web, a single strand in a tapestry stretching far beyond our horizon. When you gaze at the night sky, you're not just seeing stars, you're glimpsing the weave of reality itself, a structure so immense it took 13 billion years to build, and yet, in cosmic terms, is still just getting started. What if everything we know, every galaxy, every law of physics, every fundamental constant isn't the only possible version of reality? The Multiverse Hypothesis dares to suggest that our universe might be just one bubble in an infinite cosmic foam, where other universes exist with completely different rules. Picture a vast cosmic library where each book has its own unique set of physical laws, some with gravity so weak atoms never form, others where time runs backward, or where light travels at a different speed. Our universe, with its precise balance allowing stars, planets, and life, might be one rare volume in a collection of mostly empty or chaotic pages. This isn't just science fiction, it's a serious scientific frontier born from the math of cosmic inflation. When the universe underwent that rapid expansion in its first moments, some theories suggest it could have created pocket universes with disconnected space-time, each cooling into its own distinct reality. String theory takes it further, proposing a landscape of possible universes with different dimensions and particle properties. Even quantum mechanics hints at parallel realities where every possible outcome of an event actually happens, just in separate, branching timelines. But how could we ever prove something so mind-bending? Scientists look for clues in the cosmic microwave background, subtle anomalies that might reveal collisions with other universes. Others search for mathematical consistency, asking whether the multiverse is the only way to explain why our universe's constants are so finely tuned for life. If gravity were slightly stronger, stars would burn out too fast. If the weak nuclear force were weaker, hydrogen might never fuse into helium. The multiverse offers an answer. In an infinite ensemble of universes, a handful would, by sheer chance, have the perfect conditions for complexity. Yet the idea sparks fierce debate. Critics argue it's untestable, more philosophy than science, while proponents counter that indirect evidence could still support it. What's undeniable is how the multiverse stretches our imagination, forcing us to confront the possibility that everything we see is a tiny fraction of a much grander, stranger reality. Whether it's true or not, the hypothesis reshapes our cosmic perspective, reminding us that the universe or universes might be far wilder than we ever dreamed. String theory turns everything we thought we knew about the universe inside out, literally. Imagine zooming in on an electron so close that it's no longer a tiny dot but a shimmering loop, vibrating like a guitar string. That's the radical idea at the heart of this theory. All fundamental particles aren't points but tiny, one-dimensional strings, each vibrating at a unique frequency to create the symphony of matter and forces we observe. But here's where it gets even wilder. These strings don't just exist in the 3 dimensions we know. They ripple through a cosmos with 10 or even 11 dimensions, most curled up so tightly we'd never notice them. What does this have to do with the Big Bang? For decades, physicists hit a wall when trying to describe the universe's earliest moments. General relativity paints a vivid picture of expanding space and time, while quantum mechanics dives into the subatomic frenzy, but the two frameworks utterly collapse when forced to work together. String theory bridges this divide, offering a mathematical playground where gravity and quantum forces can finally shake hands. Some versions even suggest the Big Bang wasn't a singular explosion, but a collision of higher dimensional membranes floating in a larger multiverse that sparked our cosmos into being. Think of it like this: if our universe is a sheet of paper, the Big Bang might have been the moment another sheet brushed against it, transferring energy that ignited space, time, and matter. This ekpyrotic universe model sidesteps the need for a singularity, proposing instead that our universe is cyclical, born from collisions in a higher dimensional arena. Other string theorists argue the Big Bang was a quantum bounce, where a previous collapsing universe rebounded into expansion like a ball hitting the floor. Yet for all its elegance, string theory remains controversial. No experiment has yet confirmed its predictions, and the math is so complex it's been compared to navigating a labyrinth blindfolded. Critics argue it's more philosophy than physics, a beautiful idea without proof. But supporters counter that its very ambition is its strength. By weaving gravity into the quantum tapestry, string theory might finally answer why the universe's laws seem so finely tuned for life. Those extra dimensions, they could explain why gravity is absurdly weaker than other forces. Perhaps it's leaking into other layers of reality. The most tantalizing possibility. String theory might erase the before the Big Bang. If time itself emerged from the collision of brains or the vibrations of strings, asking what came before could be as meaningless as asking what's north of the North Pole. Our entire cosmic story might be just one verse in an endless string symphony, playing across dimensions we're only beginning to imagine. Whether it's the final theory or a stepping stone to something deeper, one thing's certain: it's rewriting the rules of existence itself. Those first quantum fluctuations were so small you'd need a microscope to see them, if they'd even been visible at all. Think of the early universe as a perfectly still pond, its surface smooth as glass. Then imagine someone tossing in a handful of subatomic pebbles, each one sending out ripples smaller than an atom's width. That's the scale we're dealing with: random, fleeting blips in the fabric of reality, popping in and out of existence thanks to the weirdness of quantum mechanics. Yet these minuscule wrinkles held the blueprint for everything we see today. Here's how it happened. During cosmic inflation, space stretched so rapidly that those quantum ripples got locked in and magnified to cosmic proportions. Picture sketching a tiny squiggle on a deflated balloon, then blowing it up to the size of a stadium. The once imperceptible wobble becomes a towering wave. In the same way, inflation took quantum jitters and stretched them into slight variations in density across the universe. Some regions ended up with a handful more particles than others, creating gravitational pits where matter could gather. Over billions of years, those pits grew deeper, pulling in gas and dust until galaxies, stars, and planets took shape. The miracle lies in the numbers. Those initial fluctuations amounted to differences of just 1 part in 100,000, like adding a single extra grain of sand to a beach. Yet that microscopic imbalance was enough to break the universe's symmetry, giving gravity something to work with. Without it, matter would have remained perfectly spread, leaving no seeds for structure, no galaxies, no stars, no planets, just an endless, featureless fog of hydrogen. What's even more astonishing is how precise these fluctuations had to be. Too weak, and gravity wouldn't have had enough clumpiness to build galaxies. Too strong, and matter might have collapsed into black holes before stars could form. Instead, the universe struck a perfect balance, weaving randomness into order on the grandest scale imaginable. Today, we see their fingerprints everywhere. The cosmic microwave background shows temperature variations that mirror those ancient density ripples. Galaxy clusters trace the same web-like patterns predicted by quantum physics. Even the empty voids between galaxies are part of the story, stretches where those early fluctuations left less matter to gather. Every structure, from the tiniest dwarf galaxy to the largest supercluster, owes its existence to quantum noise amplified by inflation. So next time you hear about quantum mechanics sounding abstract or irrelevant, remember this: the same rules that govern particles in a lab once shaped the cosmos itself. The universe didn't start with grand designs. It began with whispers, tiny tremors in the dark that grew into the symphony of light we call home. Black holes aren't just cosmic vacuum cleaners. They're master sculptors, shaping the universe in ways we're only beginning to understand. Picture a star 20 times more massive than our Sun, burning through its fuel in a fiery blaze until gravity takes over. In its final moments, it collapses inward with such force that space-time itself twists into a knot, creating a gravitational pit so deep not even light can escape. But this stellar death isn't the end, it's the birth of an engine that will influence entire galaxies. Take supermassive black holes, lurking at the hearts of nearly every large galaxy like silent titans. These behemoths, millions or even billions of times heavier than our Sun, didn't just appear, they grew over eons, feasting on gas, dust, and unlucky stars that strayed too close. Their immense gravity doesn't just hold galaxies together, it orchestrates them. Jets of superheated particles shoot from their poles at nearly light speed, carving out vast bubbles in surrounding gas that can trigger or suppress the birth of new stars. It's a cosmic feedback loop. Too much activity from the black hole heats up star-forming gas, shutting down stellar nurseries. Too little, and gas cools into dense clouds where stars ignite like fireworks. Some of these giants might be relics from the universe's infancy. Before the first stars even formed, primordial gas could have collapsed directly into black holes, seeding galaxies from the very beginning. Others might have grown through countless mergers, their gravity dictating the fate of everything around them. When two galaxies collide, their central black holes eventually spiral together in a gravitational dance, sending shockwaves through space that rearrange entire star systems. What's truly astonishing is how these dark giants leave fingerprints across cosmic time. The light from quasars, supermassive black holes devouring matter at blinding rates, has traveled billions of years to reach us, offering snapshots of the early universe. Even the Milky Way's quiet center, with its sleeping giant Sagittarius, a star, hints at past outbursts that shaped our galactic neighborhood. Without black holes stirring the pot, galaxies might never have evolved into the diverse structures we see today. Proof that sometimes the darkest forces create the brightest legacies. Yet the story doesn't end there. Some theories suggest black holes could be portals to entirely new physics, their singularities hiding clues about the universe's deepest mysteries. From Hawking radiation slowly evaporating them over eons to the mind-bending possibility of wormholes threading space-time, these cosmic paradoxes remind us that destruction and creation are two sides of the same coin. Every galaxy, every star, even the atoms in your body, might owe their existence to the chaotic influence of these gravitational maestros, silent architects weaving order from the void. The universe's ultimate fate hinges on a cosmic tug of war between two invisible giants, dark energy's relentless push and gravity's stubborn pull. Right now, the scales tip decisively toward expansion. Galaxies race apart faster with each passing moment, their light stretching into infrared oblivion as dark energy dominates the cosmos. If this continues, the universe faces a slow but inevitable fade, a heat death, where stars exhaust their fuel, black holes evaporate, and space becomes a vast, near-empty graveyard chilled to absolute zero. Picture a campfire dwindling to embers, then ash, then nothing but cold, still air. That's the bleak yet strangely peaceful end awaiting our universe if current observations hold true. But the story might not be so simple. Dark energy, the mysterious force driving this accelerated expansion, still guards its secrets. What if it isn't constant, as Einstein's cosmological constant suggests? Some theories propose dark energy could grow stronger over time, escalating its push until it overpowers even the nuclear forces holding atoms together. In this nightmare scenario called the Big Rip, galaxies, stars, and eventually planets would be torn apart. Molecules, then atoms, then quarks themselves would be shredded by the stretching fabric of space. The universe wouldn't just grow cold, it would dissolve into a sea of disconnected particles, each forever alone in an ever-widening void. Then there's the tantalizing alternative, the Big Crunch. Imagine dark energy weakening or even reversing its effect, allowing gravity to finally win the battle. Galaxies would slow their flight, then begin falling back toward each other in a cosmic reversal of the Big Bang. Space would heat up as matter compresses, stars colliding in brilliant flashes until everything merges into a seething, singular fireball, a mirror image of the universe's explosive birth. Some theories even suggest this could trigger a new Big Bang, birthing a fresh universe in an endless cycle of expansion and collapse. It's a poetic idea, death becoming rebirth on the grandest scale. The evidence, though, leans heavily toward heat death. Measurements of distant supernova, the cosmic microwave background, and the large-scale structure of galaxies all point to an expansion without end. Even the universe's geometry, flat as far as we can measure, suggests there isn't enough mass to ever pull everything back together. But science thrives on uncertainty. Dark energy's true nature remains elusive, and until we understand it fully, the door stays open for surprises. Perhaps hidden dimensions or undiscovered physics could rewrite the cosmic rulebook. What's humbling is realizing how much of this story lies beyond human timescales. Heat death wouldn't begin for trillions of years long after the last stars flicker out. A big crunch, if possible, would take even longer. Yet these distant possibilities shape our understanding of reality today. They force us to confront the universe's impermanence, to marvel at the fleeting brilliance of stars and galaxies against the backdrop of deep time. Whether the cosmos ends in fire, ice, or something beyond our imagination, one thing's certain: we're living in its golden age, a brief window where the universe is alive with light, structure, and the potential for discovery. While the Big Bang theory has become the cornerstone of modern cosmology, it wasn't the only idea on the table, and for some scientists it still isn't. Let's rewind to the early 20th century, when astronomers first realized the universe was expanding. That discovery sparked a debate. If space is stretching, does that mean it had a definite starting point, or could it be eternal? Enter the steady-state theory, a bold alternative that captured imaginations for decades. Picture a universe with no beginning and no end, where matter continuously materializes out of nothing to fill the gaps as galaxies drift apart. It's like a river that never runs dry, always replenishing itself to maintain the same density over infinite time. For its proponents, this elegant idea avoided the thorny question of a cosmic singularity. No Big Bang meant no awkward creation moment to explain. But evidence began stacking up against steady state. The cosmic microwave background, that faint glow from the early universe, was a fatal blow. Steady state couldn't explain why space was bathed in this uniform radiation, but the Big Bang predicted it perfectly. Then there was the sheer abundance of quasars, extremely bright galactic cores found only in the distant early universe. If the cosmos were truly unchanging, these objects should exist everywhere, not just in the past. By the 1970s, most astronomers had moved on, though a small group of holdouts still explore refined versions of the theory today. Then there's the cyclic model, a mesmerizing twist on cosmic origins. Imagine two parallel universes, invisible to each other, floating in a higher dimensional space. Every trillion years or so, they collide like cymbals clashing, releasing energy that fuels a new Big Bang. This isn't science fiction, it's a serious proposal from string theory, where our universe exists on a brane, short for membrane, that periodically smacks into another. Each collision resets the cosmic clock, turning the Big Bang into just one chapter in an endless cycle of expansion, cooling, and rebirth, the appeal. It sidesteps the need for a singularity by replacing it with a collision we can describe mathematically. So why does the Big Bang remain the gold standard? Because it's the only theory that ties all the evidence together. The expanding universe, the cosmic microwave background, the abundance of light elements into a single, coherent story. Alternatives often explain one piece of the puzzle but stumble over others. That doesn't mean they're worthless. Challenging the Big Bang forces scientists to test its limits, to ask what we might be missing. After all, even the best theories are provisional, waiting for the next breakthrough to refine or replace them. What's fascinating is how these debates mirror humanity's timeless quest to understand beginnings. Ancient cultures told stories of cosmic eggs, divine battles, or endless cycles of destruction and renewal. Today, we swap myths for math, but the core question remains: where did it all come from? Whether the answer lies in a singular explosion, an eternal renewal, or something stranger still, the search itself reveals just how much we've learned and how much mystery still awaits. To grasp the Plank Epoch, we have to venture into a realm where time and space lose all meaning, a fleeting sliver of existence so brief it makes a nanosecond seem eternal. Picture this: the universe is just 10 to the power of -43 seconds old. That's a decimal point followed by 42 zeros and a 1. At this scale, the cosmos was smaller than a single atom's nucleus, yet hotter and denser than anything we can recreate, even in our most powerful particle colliders. Here, the familiar laws of physics, gravity, electromagnetism, even the sturdy rules of quantum mechanics crumble like sandcastles in a hurricane. Why does our understanding falter? Because this epoch exists at the crossroads of two contradictory giants: Einstein's theory of general relativity, which governs the vast cosmos, and quantum mechanics, which rules the subatomic world. Relativity paints gravity as the curvature of space-time, while quantum mechanics treats particles as fuzzy probabilities. But in the Planck epoch, the universe was so unimaginably compact that gravity itself must have behaved like a quantum force, flickering in and out of existence. To describe this, we'd need a theory of quantum gravity, a holy grail of physics that would unite these two frameworks into one elegant equation. Some theories, like string theory, suggest that at these energies, the very fabric of reality was a seething foam of extra dimensions popping in and out of existence. Others propose loop quantum gravity, where space-time is woven from tiny, indivisible loops. Then there's the wild idea that the Planck epoch wasn't the beginning at all, just a bridge from a previous universe that collapsed and rebounded. But without a time machine or a particle accelerator the size of a galaxy, how do we test these ideas? Clues might lie in the cosmic microwave background's faintest patterns or the gravitational waves rippling from the universe's infancy. Some physicists even hunt for primordial black holes, tiny relics from that era that could have survived to today. What's certain is that the Planck Epoch isn't just a scientific puzzle, it's a frontier. Decoding it wouldn't just explain the Big Bang, it would rewrite our understanding of reality itself, revealing whether time, space, and even causality have deeper layers waiting to be uncovered. So the next time you hear someone say, "Nothing can come from nothing," remember, the Planck Epoch proves our universe didn't play by today's rules. It operated on a canvas where the impossible was mundane, and the only certainty was uncertainty. And somewhere in that chaos, the seeds of everything, from galaxies to the device in your hand, were sown. Imagine a universe where electrons zip around at the speed of light, never slowing down to form atoms. A cosmos where particles have no mass, colliding and scattering like frenzied fireflies in the dark. This could have been our reality, if not for an invisible force field that permeates every corner of existence, the Higgs field. Picture an endless ocean filling all of space, its currents unseen but its effects undeniable. Just as wading through water slows you down, particles moving through this field experience resistance, a drag that we perceive as mass. This cosmic molasses didn't always exist. In the universe's first trillionth of a second, temperatures soared above a quadrillion degrees, so extreme that the Higgs field flickered in and out of existence like a candle in a hurricane. Particles raced around massless, unburdened by gravity's pull. But as the cosmos expanded and cooled, something remarkable happened. The Higgs field stabilized like a vast blanket settling over the newborn universe. Suddenly, particles that interacted strongly with it, like quarks and electrons, began to slow, acquiring the heft needed to clump together. Those indifferent to the field, like photons, remained weightless, forever racing through space at light speed. Why does this matter? Because mass isn't just a number on a scale, it's the architect of reality. Without it, gravity would have nothing to work with. No stars could ignite, no planets could coalesce, no chemistry could unfold. Electrons would never settle into orbits around atomic nuclei, leaving the universe a formless soup of unattached particles. Even time and space would behave differently, their fabric woven by interactions between mass and energy. The Higgs field is the silent choreographer behind the universe's structure, determining which particles get to play leading roles and which remain fleeting extras. Yet the Higgs field isn't uniform like a flat sheet. It's more like a bumpy terrain with valleys and peaks where particles experience different levels of drag. The Higgs boson, discovered in 2012 at the Large Hadron Collider, is essentially a ripple in this field, a fleeting disturbance that confirms its existence. Finding it was like spotting the wake of a ship in foggy waters, proof that something vast and hidden moves beneath the surface. What's astonishing is how delicate this balance had to be. If the Higgs field were slightly weaker, particles would be too light for gravity to sculpt galaxies. Stronger, and atoms might collapse into dense clumps, leaving no room for the complexity that leads to stars, planets, or life. Its precise value seems almost tailor-made for our existence, a cosmic coincidence that still keeps physicists awake at night. Whether this tuning is mere luck or a clue to deeper laws remains one of physics' greatest mysteries. So the next time you pick up an object and feel its weight, remember, you're not just sensing gravity's pull, you're feeling the whisper of a field that emerged in the universe's fiery infancy, a hidden hand that shaped everything from the tiniest atom to the grandest galaxy. Without it, the cosmos would be a shadow of itself, a place without form, without structure, without us. Neutrinos are the universe's ultimate ghosts, particles so elusive they can pass through a light year of lead without a single collision. Born in the fiery chaos just 1 second after the Big Bang, these nearly massless phantoms have been streaming through space and straight through you, ever since, carrying whispers from the universe's earliest moments. Every second, trillions of them from the sun alone zip through your body like cosmic bullets, leaving no trace behind. Their reluctance to interact with matter makes them maddeningly hard to detect, but it's also why they're such priceless messengers. While light from distant stars gets absorbed or scattered, neutrinos travel unimpeded, delivering pristine information from places and times we can't observe any other way. What makes these shadowy particles so special? For starters, they come in three types: electron, muon, and tau neutrinos, each linked to their heavier charged cousins. But here's the twist: neutrinos don't stay in one flavor. They oscillate, morphing from one type to another as they travel. This chameleon-like behavior, discovered only in the late 20th century, proved they have mass, something the standard model of particle physics never predicted. That tiny mass, billions of times lighter than an electron, might hold clues to why the universe contains any matter at all. See, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving nothing but energy. Yet here we are, in a cosmos dominated by matter. Neutrinos, with their subtle asymmetries, might help explain this cosmic imbalance. To catch these phantoms, scientists build detectors in places where almost nothing else can interfere, deep underground, in Antarctic ice, or at the bottom of the sea. One experiment, Japan's Super Kamiokan, uses a tank filled with 50,000 tons of ultra-pure water lined with sensitive light detectors. When a neutrino, against all odds, does interact with an atom, it creates a faint blue flash called Cherenkov radiation, a subatomic sonic boom. Other projects, like Ice Cube at the South Pole, monitor cubic kilometers of ice for neutrino strikes. These detectors aren't just fishing for random particles. They're hunting specific neutrinos from supernova, black holes, and even the Big Bang itself. The Holy Grail, detecting relic neutrinos from the cosmic neutrino background, a faint echo of the universe's first second. Unlike the cosmic microwave background, which dates to 380,000 years after the Big Bang, these neutrinos carry information from an era when the cosmos was a seething plasma of quarks and gluons. If we could capture them, it'd be like finding a recording of the universe's first cry. But there's a catch. These ancient neutrinos have cooled to just a whisper above absolute zero, their energy dwarfed by even the faintest modern neutrinos. Catching them would require detectors of unimaginable sensitivity, perhaps leveraging quantum technologies not yet invented. Yet the payoff could rewrite physics. Neutrinos might hint at hidden dimensions, reveal why matter dominates antimatter, or even expose flaws in our understanding of gravity. Some theories suggest they could be Majorana particles, their own antimatter twins, a property that might explain why the universe has so little antimatter left. Others speculate that sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, could be the key to dark matter. Every time we think we've pinned neutrinos down, they surprise us, slipping through our theories like they slip through solid rock. So the next time you feel an inexplicable shiver, remember, it might just be a neutrino from the dawn of time, whispering secrets as it passes through you untouched. These spectral particles, born in the universe's first breath, are still shaping our understanding of reality, one elusive interaction at a time. One of the most baffling mysteries in cosmology isn't about what exists, it's about what shouldn't. According to every known law of physics, the Big Bang should have created equal amounts of matter and antimatter, particles and their mirror opposites with identical mass but opposite charge. When these pairs meet, they annihilate in a flash of pure energy. So why, in a universe that began with this perfect symmetry, does everything we see, from distant galaxies to the screen in front of you, consist entirely of matter? This cosmic imbalance, known as baryogenesis, isn't just a quirk of nature, it's the reason anything exists at all. Let's rewind to the universe's first microseconds. A seething plasma of quarks, antiquarks, electrons, and positrons filled every corner of space, colliding and annihilating in a relentless dance. For every billion matter-antimatter pairs, calculations suggest just one extra quark survived. That razor-thin surplus, a rounding error in the grand equation of the cosmos, became the raw material for every star, planet, and living thing. The question is, what tipped the scales? Three key conditions had to break nature's perfect symmetry. First, the universe needed processes that treated matter and antimatter slightly differently, a violation called CP symmetry breaking. Imagine shaking two nearly identical soda cans, one of which fizzes slightly more than the other when opened. In 1964, scientists observed this tiny asymmetry in particles called kaons, proving antimatter doesn't always mirror matter perfectly. Later, experiments with B mesons revealed even stronger imbalances, but still far too small to explain the universe's overwhelming matter dominance. The second requirement was a departure from thermal equilibrium, a moment when the universe's expansion outran particle interactions, freezing in that slight matter excess before annihilation could erase it. Picture a boiling pot left on the stove too long. As the water evaporates, a few stubborn bubbles get trapped at the rim. In the early cosmos, rapid cooling may have similarly trapped leftover matter when antimatter ran out of partners to annihilate. Finally, interactions had to violate baryon number conservation, a rule that normally prevents matter from being created or destroyed wholesale. Certain grand unified theories predict proton decay, a process where matter slowly unravels over eons. If protons can decay, they might also have formed asymmetrically in the universe's infancy. Yet even with these pieces, the puzzle remains unsolved. Current particle physics can't account for the degree of matter's dominance. Some theories point to neutrinos, those ghostly particles that may be their own antimatter opposites. Others suggest primordial black holes devoured antimatter preferentially, or that hidden fields tilted the balance during cosmic inflation. The answer might lie in physics beyond the standard model, perhaps supersymmetry or extra dimensions. What's at stake isn't just academic. If antimatter had won, or if the balance had been perfectly even, the universe would be empty, devoid of atoms, light, or life. That fragile one in a billion asymmetry wasn't just a fluke. It was the universe's first and most consequential lottery win. And until we uncover why the cosmic dice rolled in matter's favor, the story of our existence remains deliciously incomplete. The cosmic microwave background isn't just a faint glow, it's a time machine. Picture the universe at just 380,000 years old, a toddler by cosmic standards. Space was no longer a searing plasma, but had cooled enough for atoms to form, allowing light to break free from its chaotic dance with matter. That first burst of liberated photons has been traveling ever since, stretched and cooled by the expansion of space into the microwave whisper we detect today. But this isn't just ancient radiation, it's a baby photo of the cosmos, capturing the moment it transitioned from opaque fireball to transparent universe. What makes the CMB so revolutionary are the tiny imperfections etched into its glow. While it appears nearly uniform to the naked eye, sensitive instruments like NAS, a WMAP, and the European Space Agency's Planck satellite have mapped temperature variations as subtle as 1 part in 100,000. These fluctuations, some slightly warmer, others cooler, aren't random noise. They're the fingerprints of quantum, ripples from the universe's first moments, stretched to cosmic proportions by inflation. Think of them as cosmic breadcrumbs, marking where matter was ever so slightly denser. creating gravitational wells that would eventually pull in gas to form galaxies, stars, and planets. The precision of these measurements is staggering. The CMB's temperature hovers at just 2.725 degrees above absolute zero, a relic of the universe's cooling over 13 billion years. Yet within that frigid glow, patterns emerge like ink blots on a cosmic Rorschach test. The distribution of hot and cold spots reveals the universe's geometry, composition, and even its fate. For instance, the spacing between these fluctuations confirmed that space is flat to within a fraction of a percent, a critical clue that the universe's total mass-energy density is perfectly balanced, neither collapsing nor tearing apart too quickly. But the CMB isn't just about temperature. Polarization, the slight twisting of light waves, carries its own secrets. Some patterns, called B modes, could betray the gravitational waves unleashed during inflation, offering direct evidence of the universe's explosive growth spurt. Others hint at the neutrino background, the ghostly echo of particles that slipped free even before the CMB formed. Each layer of analysis peels back another chapter of cosmic history, turning this faint microwave hum into a Rosetta Stone for decoding the universe's origins. What's truly humbling is realizing that this radiation has been bathing Earth since long before humans existed or even before Earth itself formed. The static on an old-fashioned TV. About 1% of that snow comes from the CMB, a whisper from the dawn of time mingling with modern signals. Every time we map it more precisely, we're not just studying the past, we're testing the limits of physics itself, probing energies and conditions so extreme they'll never exist again. The cosmic microwave background is more than a relic. It's a living archive, still revealing secrets about how everything began. Gravitational waves aren't just cosmic messengers from colliding black holes. They could be time capsules from the universe's birth. If cosmic inflation really happened, the violent stretching of space in those first moments should have sent tremors rippling through the fabric of space-time itself. These aren't the gravitational waves we've detected from star collisions, but something far more ancient, primordial gravitational waves, carrying whispers from a time before the first particles even existed. Imagine space-time as a vast, still lake. When inflation occurred, it would have been like dropping a mountain into that lake, an event so colossal it sent waves surging outward in every direction. These ripples wouldn't be made of water, but of distortions in the very geometry of reality, compressing and stretching space as they traveled. Unlike light, which scatters and fades, gravitational waves pass through everything almost untouched, meaning they could carry pristine information from the universe's first trillionth of a second. The challenge: these waves would be absurdly faint by now, their signals stretched and diluted over billions of years, but there's a clever way to spot them. As these primordial waves passed through the early universe, they would have subtly polarized the cosmic microwave background, twisting its light in a distinct pattern known as B-mode polarization. It's like finding fingerprints on a windowpane, evidence of something powerful passing through. Experiments like BICEP and the South Pole Telescope have hunted for this telltale swirl, but so far, dust in our own galaxy has muddied the signal. Future missions, like the proposed Light-Bird satellite, aim to filter out this interference, scanning the skies with unprecedented sensitivity. What's at stake isn't just confirming inflation, it's peering into energies a trillion times beyond what any particle collider could reach. The strength and frequency of these waves could reveal whether inflation was driven by a single quantum field or a more complex interplay of forces. Some theories even suggest primordial waves might carry traces of extra dimensions or exotic physics from before the Big Bang. It's a long shot, but if we detect them, It would be like uncovering the universe's first scream, a direct line to the moment everything began. Until then, the hunt continues, with scientists refining detectors and sifting through data for the faintest hints of spacetime's earliest tremors. Finding these waves wouldn't just fill in a blank in our cosmic story, it would rewrite the first chapter entirely. The universe shouldn't work, at least not for us. Tweak any of nature's fundamental constants just slightly, and reality as we know it would unravel. If the strong nuclear force were 2% stronger, protons would bind so tightly that stars would burn out in seconds. If gravity were a fraction weaker, galaxies might never have formed. Even the vacuum energy of empty space is precariously balanced a hair more, and the cosmos would have torn itself apart before atoms could bond. This uncanny fine-tuning isn't just a curiosity, it's the foundation of our existence, and it's led scientists to a profound question: why does the universe seem tailor-made for life? This is the heart of the anthropic principle, the idea that the universe's laws appear fine-tuned because we're here to observe them. Think of it like a cosmic version of survivor bias. Imagine a puddle marveling at how perfectly its shape fits the hole it's in. The hole wasn't designed for the puddle simply conforms to what's there. Similarly, we might not be living in a universe designed for life, but in one of the rare pockets where conditions accidentally allow it. But this raises even bigger questions. Could there be countless other universes out there, each with different physical laws, most barren, but a rare few like ours just right? This multiverse theory turns fine-tuning from a miracle into a statistical inevitability. If infinite universes exist with random constants, eventually one would hit the jackpot. It's like shuffling a deck of cards forever. Sooner or later, you'll deal a perfect hand. Yet not everyone finds this satisfying. Some scientists argue the anthropic principle is a cop-out, a way to avoid explaining why our universe's constants have the precise values they do. Others propose deeper laws, a theory of everything, that might naturally lead to life-friendly conditions. For instance, string theory's landscape of possible universes suggests physical constants aren't arbitrary, but emerge from higher dimensional geometry. Then there's the philosophical twist. Does the universe's fine-tuning imply a designer? While some see this as evidence of intentional creation, others counter that invoking a designer just kicks the mystery up a level. If a creator fine-tuned the universe, who fine-tuned the creator? What's undeniable is how fragile our existence is. The universe didn't have to be this way, yet here we are, pondering its mysteries. Whether through multiverses, undiscovered physics, or sheer luck, the anthropic principle forces us to confront our place in the cosmos, not as its center, but as fleeting witnesses to a reality that, against all odds, allows us to exist at all. At the universe's birth, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, weren't separate at all. They existed as a single, unified superforce, a perfect symmetry where all interactions were indistinguishable. Picture a spinning coin before it lands. In that blur of motion, heads and tails don't exist yet. There's only the symmetry of rotation. The early universe was like that coin, with all forces merged into one elegant, balanced state. But as the cosmos expanded and cooled, this symmetry shattered like ice cracking under pressure, giving rise to the distinct forces that shape our reality. The first breakup happened almost instantly, at temperatures exceeding 10 to the power of 28 degrees, so hot that numbers lose meaning. Gravity peeled away from the other forces. This separation wasn't a clean break, but more like a phase transition, similar to how water suddenly turns to ice when cooled past a critical point. With gravity now independent, space-time itself could begin to flex and curve, setting the stage for the cosmic expansion we observe today. Next came the grand unification epoch, where the remaining three forces, electromagnetism and the strong and weak nuclear forces, remained unified. This era lasted until the universe was about a trillionth of a second old. Then, as temperatures dropped below 10 to the power of 25 degrees, the strong nuclear force broke free. This force, which normally glues quarks together inside protons and neutrons, was now distinct from the electroweak force that governed light and radioactivity. The split released enormous energy, possibly fueling cosmic inflation's explosive expansion. The final symmetry breaking occurred when the universe was roughly a trillionth of a second old. The electroweak force, now standing alone, fractured into electromagnetism and the weak nuclear force. This transition wasn't just about separation. It gave particles mass through the Higgs mechanism, like molasses thickening to slow them down. Without this critical event, electrons would zip through space at light speed, never forming stable atoms. Stars wouldn't shine, molecules wouldn't bond, and life as we know it would be impossible. What's astonishing is how these fractures left cosmic fingerprints. The very unevenness we see in the universe, galaxies clustering here, voids stretching there, may trace back to quantum fluctuations amplified during symmetry breaking. Even the mysterious imbalance between matter and antimatter could stem from slight asymmetries in how these forces decoupled. The forces didn't just separate, they left behind a universe rich with structure, complexity, and the potential for life. Yet hints of that primordial unity linger. Particle colliders like the Large Hadron Collider briefly recreate electroweak unification energies, letting us glimpse the universe's symmetric past. And some theories suggest that under extreme conditions like inside black holes or at the Big Bang itself, these forces might reunite, revealing a deeper truth, that nature's apparent complexity is just fragments of a simpler, more beautiful whole. The universe's symmetries didn't vanish, they're hidden in plain sight, waiting for us to piece them back together. The question of what happened before the Big Bang is like asking what's north of the North Pole. It might not even make sense in the framework of our universe. Time as we understand it began with the Big Bang, so talking about a before could be as meaningless as searching for the edge of a round Earth. Yet the human mind rebels at the idea of absolute beginnings. We instinctively crave cause and effect, a chain of events stretching backward so naturally. Theorists have devised some astonishing ways to sidestep this cosmic conundrum. One radical idea comes from loop quantum gravity, which suggests the Big Bang wasn't a true beginning but a rebound. Imagine the collapsing universe before it as a stretched rubber band instead of snapping. It reaches a point of maximum compression and springs back outward in what we call the Big Bang. In this scenario, time doesn't begin or end. It cycles eternally between expansion and contraction, each bang preceded by a crunch. There's no singularity, no point where physics breaks down, just an endless cosmic heartbeat. Then there's the ekpyrotic universe model from string theory, where our Big Bang was really a collision between two higher dimensional membranes or branes floating in a larger space. Think of it like two sheets of paper smacking together in a windy room. The energy of that impact became the fireball of our expanding universe. In this view, the before was another universe, quietly existing parallel to ours until the moment of collision reset the cosmic clock. Even more mind-bending is Roger Penrose's conformal cyclic cosmology, which proposes that the distant future of one universe becomes the Big Bang of the next. As black holes evaporate and particles lose mass over trillions of years, the universe becomes indistinguishable from its initial state, a smooth, empty expanse ready to bang again. Time loses all meaning at these extremes, allowing the end of one cycle to seamlessly become the beginning of another without a true starting point. Yet some physicists argue we're asking the wrong question entirely. If time emerged with the Big Bang, then phrases like "before the Big Bang" are as nonsensical as "south of the South Pole." Quantum gravity theories like causal dynamical triangulation suggest time might be granular, emerging from more fundamental building blocks the way temperature emerges from atomic motion. In this view, time isn't a backdrop to the universe, it's a side effect, a collective illusion woven from deeper, timeless physics, the most unsettling possibility. That our universe is a bubble in an eternal, multiverse foam, where countless universes pop into existence with random physical laws. Some last microseconds before collapsing, others, like ours, strike the perfect balance for longevity. In this sea of cosmic randomness, asking what came before is like a fish asking what existed before the ocean. There might not be an answer that fits within our limited framework. What unites these theories is their audacity. Each one rewrites our understanding of time, causality, and existence itself. Whether cyclical, emergent, or part of a vaster multiverse, the pre-Big Bang landscape remains the ultimate frontier of cosmology. Until we uncover quantum gravity's secrets or detect echoes of a prior universe in the cosmic microwave background, the question lingers: is our universe a one-time event, or just one note in an infinite cosmic symphony? To understand the universe, we don't just peer through telescopes, we build entire cosmos from scratch inside supercomputers. These aren't video game simulations, but painstakingly precise mathematical reconstructions, where every particle, every force, every law of physics is encoded into lines of software. The goal: to rewind time, fast-forward evolution, and test our wildest cosmic theories in digital laboratories where the only limit is processing power. Take the Illustris TNG project, one of the most ambitious virtual universes ever created. Running on some of the world's fastest supercomputers, it simulates a cube of space over 13 billion light-years wide, tracking trillions of particles as they clump into galaxies under gravity's pull. The simulations don't just mimic what we see, they predict details telescopes haven't spotted yet, like how magnetic fields weave through galaxy clusters or why some galaxies stop forming stars prematurely. When astronomers compare these virtual skies to real observations, the matches are often eerily precise, like finding a photograph of someone you've only ever drawn from imagination. Dark matter's role becomes starkly clear in these simulations. Without its invisible scaffolding, galaxies simply wouldn't form as they do. Supercomputers reveal how dark matter's gravity creates vast halos where ordinary matter collects, like dew condensing on a spider's web. Yet mysteries remain. Some simulations produce galaxies with too many satellite companions compared to reality, hinting that dark matter might interact with itself in ways we haven't accounted for. Others suggest early black holes could have stunted galaxy growth, solving long-standing puzzles about why some galaxies seem older than they should be. The Big Bang itself gets a digital reenactment. Projects like the Cosmic Dawn Initiative simulate the universe's first billion years, capturing the flicker of the first stars igniting in the darkness. These cosmic renaissance simulations show how ultraviolet light from early stars ripped electrons from atoms in a process called reionization, transforming the universe from opaque to transparent. Without supercomputers, we'd have no way to test whether our theories about this epoch hold water, or if we're missing a fundamental piece of the puzzle. But crafting these digital universes isn't just about raw computing muscle. It's a delicate dance between accuracy and approximation. Simulating every atom is impossible, so scientists use clever shortcuts like treating groups of stars as single superparticles or modeling gas dynamics with fluid equations. Even then, a single simulation can take months to run, consuming millions of processor hours. The resulting datasets are so vast that analyzing them requires AI tools originally designed for facial recognition, except here, they're spotting patterns in galaxy formation instead of human features. What's truly revolutionary is how these simulations let us experiment with alternate realities. Want to see what happens if dark matter is warmer or more interactive? Adjust the code and hit Run. Curious how the universe would look if inflation happened differently? Rewind the virtual clock and tweak the initial conditions. These cosmic what-ifs aren't just academic exercises, they help astronomers prioritize which real-world observations could confirm or debunk our deepest theories. The ultimate dream, a simulation so accurate it predicts phenomena before telescopes detect them. We're not there yet, but with each leap in computing power, our digital universes grow richer, more detailed, and more revealing. They remind us that the cosmos isn't just something we observe, it's something we can, in a way, recreate one line of code at a time. The dream of a theory of everything isn't just some lofty academic pursuit, it's the culmination of centuries of scientific discovery, a quest to distill the universe's complexity into a single, elegant framework. Imagine if all the forces we know, gravity, electromagnetism, the strong and weak nuclear forces, could be traced back to one fundamental equation, a cosmic Rosetta Stone unlocking the deepest secrets of existence. This isn't about tidying up physics textbooks, it's about uncovering the primal rules that birthed the universe itself. At the heart of this quest lies a glaring paradox. On one hand, quantum mechanics flawlessly explains the subatomic world, where particles flicker in and out of existence like fireflies in the dark. On the other, Einstein's general relativity paints gravity as the curvature of spacetime, shaping galaxies and black holes with breathtaking precision. Yet these two titans of physics clash violently when forced to work together. Near a black hole's singularity or in the universe's first moments, their equations explode into nonsense, revealing a chasm in our understanding. A theory of everything would bridge that divide, revealing how gravity dances with quantum forces at the tiniest scales. String theory has long been the leading contender. Its vision of vibrating, multidimensional strings offers a way to unify all particles and forces as different notes on a cosmic symphony. But critics argue it's too abstract, with predictions impossible to test using current technology. Loop quantum gravity takes a different approach, proposing spacetime itself is woven from tiny, indivisible loops, a pixelated universe where gravity emerges from quantum knots. Then there's emergent gravity, suggesting gravity isn't fundamental at all but arises from deeper, hidden layers of reality, like temperature emerging from atomic motion. The stakes couldn't be higher. A true theory of everything wouldn't just reconcile quantum mechanics and relativity, it might rewrite the Big Bang's origin story. Some models suggest the singularity was a quantum bounce, a rebound from a previous collapsing universe. Others hint at a multiverse bubbling with alternate realities, each with different physical laws. If we could peer beyond the Plank Epoch, that unfathomably brief moment after creation, we might find clues etched in gravitational waves or hidden dimensions. Yet the search is as philosophical as it is mathematical. What if the universe's laws aren't inevitable but accidental, frozen into place during cosmic inflation like cracks in cooling glass? Or what if reality is fundamentally computational, with space-time and forces emerging from some deeper code? Every failed experiment and mathematical dead end teaches us something profound, not just about the universe, but about the limits of human imagination. For now, the theory of everything remains just out of reach, a shadow flickering at the edge of comprehension. But with each breakthrough, from quantum entanglement to black hole thermodynamics, we catch glimpses of a grander scheme. Whether the answer lies in strings, loops, or something beyond our current paradigms, one thing's certain: the day we unlock it, we won't just understand how the universe began. We'll finally see our place within it. Long before telescopes and particle accelerators, humans grappled with the universe's origins through stories, logic, and sheer contemplation. Ancient Greek philosophers like Thales rejected mythological explanations, proposing instead that water was the fundamental substance from which all things arose, an early attempt to unify reality under a single principle. Aristotle later argued for an eternal universe with no beginning or end, a view that dominated Western thought for centuries. These early thinkers didn't just guess blindly. They observed nature's patterns and reasoned their way toward cosmic truths, laying groundwork that would later inspire scientific inquiry. Eastern traditions approached the mystery differently. Hindu cosmology described a cyclical universe breathing in and out over vast eons, with each day of Brahma lasting over 4 billion years, a strikingly modern-seeming concept of cosmic cycles. Buddhist philosophy took it further, suggesting reality itself might be an illusion, with no definitive origin point to grasp. These weren't primitive myths but sophisticated frameworks attempting to reconcile human experience with the infinite, often foreshadowing modern multiverse theories in their embrace of boundless possibility. Theological perspectives add another layer. The Judeo-Christian concept of creation ex nihilo, out of nothing, echoes startlingly in modern quantum physics, where particles flicker into existence from apparent emptiness. Islamic scholars like Al-Ghazali debated whether time itself was created, anticipating contemporary debates about whether "before the Big Bang" is a meaningful phrase. These traditions often frame the universe as intentional, a designed artifact rather than accidental fluctuation, raising profound questions about purpose that science alone can't address. Where science and philosophy collide most dramatically is on the nature of causality. The Big Bang seems to demand a cause, yet physics shows how quantum events can occur without one. Some philosophers argue this lets the universe be its own cause, while theologians see divine action in the fine-tuning of physical constants. The principle of sufficient reason, that everything must have an explanation, battles with brute fact realism, the idea that some things just are. These aren't abstract word games but vital struggles to define what counts as an explanation when confronting ultimate origins. Modern philosophy of science probes even deeper. Is the Big Bang narrative a true description of reality, or just our best current model? Could multiple origin stories, scientific, theological, philosophical, coexist as complementary perspectives rather than rivals? The multiverse hypothesis, for instance, transforms the fine-tuning debate by suggesting our universe's life-friendly constants might be a statistical fluke among infinite others. This shifts the philosophical question from why these laws to why this selection mechanism, a subtle but profound reframing. Perhaps the most enduring contribution of philosophy is its insistence that origins can't be disentangled from meaning. Science tells us how hydrogen condensed into galaxies, but not why that story matters to conscious beings who emerged from stardust to tell it. The awe we feel when peering at Hubble Deep Field images or pondering quantum vacuums isn't just curiosity. It's the latest chapter in humanity's oldest dialogue between observation and wonder, between mechanism and mystery. In this light, every scientific paper on cosmic inflation is also a philosophical statement, whether its authors realize it or not. What unites these diverse approaches is humility. Just as dark matter reminds us most of the universe is invisible, philosophy and theology remind us that even our sharpest scientific tools have limits when facing the ultimate question. The Big Bang's afterglow may illuminate cosmic history, but human thought, with all its contradictions and creativity, still lights the path to understanding what that history truly means. We're standing on the brink of a new era in cosmic exploration, where cutting-edge instruments will peer deeper into the universe's infancy than ever before. The James Webb Space Telescope, with its gold-coated mirrors and infrared eyes, acts like a time machine tuned to the universe's toddler years. Unlike Hubble, which showed us galactic adolescence, Webb captures the faint glow of the very first stars and galaxies as they flickered to life in the primordial dark. These ancient structures shouldn't exist according to some models. Their surprising brightness and maturity could force us to rewrite entire chapters of cosmic evolution. But Webb is just the beginning. The European Space Agency's Euclid mission maps dark matter's invisible web across billions of light-years, tracing how its gravitational scaffolding shaped galaxy formation. NASA's upcoming Nancy Grace Roman Space Telescope will survey vast cosmic volumes, hunting for primordial black holes that might be inflation's smoking gun. Meanwhile, ground-based behemoths like the extremely large telescope in Chile will analyze the atmospheres of exoplanets orbiting ancient stars, probing whether life's ingredients existed in the universe's first generations. Particle physics joins this cosmic detective story with machines like the Future Circular Collider, a proposed successor to the Large Hadron Collider that would smash particles at energies not seen since the universe's first trillionth of a second. Such experiments might recreate exotic states of matter that filled the primordial cosmos, or even discover new particles that could explain dark matter's identity. Deep underground, detectors like Darwin hunt for ultra-rare interactions that might reveal why matter triumphed over antimatter in the universe's first moments. The most audacious ideas stretch beyond conventional physics. Projects like the Laser Interferometer Space Antenna LISA will detect gravitational waves from supermassive black hole collisions, potentially catching echoes of cosmic inflation. Quantum sensors in Antarctica and space-based observatories scan the cosmic microwave background for faint polarization patterns, imprints of gravitational waves from the Big Bang itself. Some theorists even propose using the Moon as a neutrino detector, leveraging its immense bulk to catch ultra-low-energy neutrinos from the universe's first second. What makes this golden age of exploration so thrilling is how each discovery interconnects. A measurement of primordial helium abundance might tweak our inflation models. An unexpected galaxy in Webb's deep fields could hint at alternative dark matter properties. The coming decade promises more than incremental progress. We're hunting for paradigm shifts, moments where the universe forces us to think differently about its origins. Every unanswered question, from the nature of dark energy to the reason for matter's dominance, represents a potential revolution waiting to happen. One thing is certain: as these missions unfold, we'll confront surprises that challenge our most cherished theories. The universe has always been richer than our imaginations, revealing layers of complexity we never anticipated. Whether we find evidence of parallel universes, crack the code of quantum gravity, or stumble upon phenomena we can't yet name, the journey to understand our cosmic beginnings is far from over. It's accelerating into uncharted territory. From the unimaginable heat of the Big Bang to the delicate dance of galaxies spinning through the void, our cosmic origin story isn't just about particles and forces. It's a reflection of humanity's relentless drive to make sense of the infinite. Every glowing star we see, every ripple in the fabric of spacetime we detect, carries echoes of that primordial moment when existence itself flickered into being. What began as a singularity smaller than an atom has unfolded over billions of years into a universe rich with complexity, capable of crafting planets, oceans, and minds curious enough to trace their own beginnings. Yet for all we've uncovered, from the quantum seeds of cosmic structure to the dark energy accelerating our expansion, the most profound realization might be how much remains hidden. The Plank Epoch's mysteries, the true nature of dark matter, the question of what preceded the Big Bang, these aren't just gaps in our knowledge. They're invitations to push further, to imagine bolder theories and build more sensitive instruments. Each time we map the cosmic microwave background or detect gravitational waves, we're not just collecting data, we're assembling pieces of a puzzle written into the fabric of reality itself. This journey hasn't been solitary. Across centuries and civilizations, stargazers, philosophers, and scientists have added threads to this grand narrative. Ancient cultures saw creation in celestial myths. Einstein reshaped gravity with his mathematics. Modern astronomers pass light from dying stars to read the universe's expansion like a cosmic fingerprint. Every breakthrough stands on the work of countless curious minds who refuse to accept "we can't know" as an answer. What's truly remarkable is how personal this story becomes when we recognize our own atoms were forged in stellar furnaces. The iron in your blood, the calcium in your bones, these elements were scattered across space by supernova explosions long before Earth existed. We're not just observers of the cosmos, we're its conscious embodiment. Stardust evolved to contemplate its own origins. So where does the story go from here? Perhaps future telescopes will catch whispers from before the Big Bang, or quantum computers will simulate alternate universes with different physical laws. Maybe we'll find that our universe is just one note in an infinite symphony of realities. Or perhaps the greatest revelation will be accepting that some questions exist beyond our grasp, and that the search itself is what gives them meaning. Now it's your turn. When you look up at the night sky, what cosmic questions ignite your curiosity? Do you think we'll ever uncover the universe's ultimate secrets, or will some mysteries remain forever beyond the horizon of human understanding? Drop your thoughts below. After all, the conversation about our origins is one we're all part of. And if you've enjoyed this journey from nothingness to everything, be sure to hit subscribe. The universe has countless more stories to tell, and we're just getting started.